Yeah, this is part two of the video about climate obstruction using a neurosymbolic architecture. So next, I'm going to walk us through an example prompt and then, show you sort of a peek behind the hood as to how what kind of what Sparkle query gets generated and how that's used. So this shows you the user interface. You can see it's pretty simple. It's a and the nice thing about this is it's all in Python on the server, and then you have in serve.io you have these fairly simple, mostly text or single parameter based widgets that you can use. It's really great for large language model driven systems because those systems are often, the main way to interact with them is via natural language. So you don't need like a lot of widgets and sliders and things like you would need with a standard kind of GUI interface. So this is what the portal looks like. There's three parameters here. The first three that the user can fill in before they make send their prompt to the LLM. And the first one, I'm kind of starting in the middle here because it's really the most important one. This is where they enter the question. And you can see in this case, the sample question we're using is, are there any conspiracy theories linking climate change and the COVID pandemic? The next parameter is the relevance threshold. So remember I was talking about, we use that cosine distance function to compare the vector that gets generated for the question with the existing vectors that we have for our corpus. And we find if there's any in the corpus that are within the relevance threshold. So this relevance threshold has to be a floating point number greater than 0 and less than 1. And the higher the number, the more the higher the match has to be between the vector and the existing vectors between the question vector and the vectors for the matching documents. So 0.7 is where we usually start. And one reason that, of course, that this is something that can be tweaked by the user is because a common thing to do is to start with a relatively high number, like 0.7, but then if you don't find any matches, you can go down to 0.6 or even 0.5, and still most of the time, even at 0.5, if you find any matches, those generate pretty good answers. So you can tweak that parameter as well. And then finally, the last parameter is number of results to show. So what that is if you have more than one document string that whose vector is within the threshold for relevance that you defined, how many of those document strings are you going to use? And in this case, we're saying 5. That number has to be an integer greater than 0 and less than or equal to 20. So you enter all three of those parameters, and then what happens behind the scenes is in that serve.io function or file that I described. One of the things we have is a bunch of text that's a template for a Sparkle query. So essentially we have all the text that you see here except for the user question, the number of results, and the relevance threshold. Those are not defined. And what happens is when the user hits enter, the interface takes those three values from the interface, it plugs them into the template for the Sparkle query, and then it has a complete Sparkle query that it can send to Allegro Graph, and then Allegro Graph will then interact with ChatGPT, send the appropriate things, and get the answer. And the thing that's doing most of the heavy lifting here is what Allegro Graph calls a magic property. And so in this case, the magic property is called LLM colon ask my documents. You can see it's kind of in the middle there of that where statement. And a magic property is something that it's a proprietary extension for Allegro Graph, and it looks like a property. So if you look there, you can see it's in the middle, which is where you would normally have a property. But in reality, what it's doing is it's calling a function. So it binds things that are in the first part, where you would normally have the predicate, and then it executes the magic property, and then that returns the bindings for the documents, the properties, and the content. And then those optional statements at the bottom there, those are completely irrelevant. Those aren't used at all in the integration with ChatGPT. Those are things that we've determined are the most likely kind of entry points that the user will want to see, in addition to seeing the document objects. And it also will usually be useful to see any values that the document has for the topic, subparts of the document, or author of the document. So, but because any given document is not guaranteed to have any or all of those. I mean, it'll usually have at least one, but it's possible to have none of those. We don't. That's why each one is its own optional statement. Because if not, then if even one of those triples was not completely instantiated, then the Sparkle query would fail, and we would get nothing, which of course we don't want to do. But then those optional matches are used by the further exploration within the graphic browser of the knowledge graph. Oh, and then also you can see though, so the user question, that's where we took the question that the user had, and then you can see down below that 5 is the number of matching documents to use, and then 0.7 was the relevance threshold. So those all got plopped into the Sparkle query, and that gave us a complete Sparkle query that we could send off to Allegro Graph, and Allegro Graph would then send it out to ChatGPT using the OpenAI API. So then the next step, remember, is okay. We can you can see the answer that there was something called the climate lockdown conspiracy. I won't go into it, but you see, it is very interesting. I mean, interesting, and it shows in how broken our system is, because it's kind of ridiculous conspiracy theory that was formed on essentially no real solid information, but was used by people to spread doubt and confusion about climate change. And so you can see, and both of the answer and the supporting documents, obviously, those are both scrollable. So you can see that we got a couple of answers and we got the supporting documents. But then also we're going to now click this View Answer Graph in Gruff, and that will take us in the Allegro Graph Gruff visualization tool. Now, this is not the exact the interface that we'll see when we hit that. When we hit that link, we'll first go into, there's several different views in Gruff, and one of them is the view which you usually start from, which is a view that allows you to type in a Sparkle query. But what we'll do, one of the things we do every time the user hits enter is we put the Sparkle query that was generated on the copy paste stack. So then when we go into Gruff, by default, we go into the view where you're meant to type in a Sparkle query. We can just do a Control V, and then that pastes the complete Sparkle query that was generated. We hit return, and that generates all the objects, that match that were used by to generate the answer, as well as those additional optional triples that matched. And in this case, this graph that I'm showing you is the graph that was originally created by default by Gruff, um, uh, given the graph that was returned by that Sparkle query that I just showed you. Now, the next step then is I used Gruff to manipulate this graph and to change it quite a bit. I think it took me about like 5 operations to get from this graph to this graph, which is quite a bit different, and it just shows you the power of Gruff. So, like one of the things I did is I said, okay, first of all, I don't want to see any properties that have literal values. You know, that's not going to lead me anywhere. So let's get rid of those. Let's just get rid of those completely. I added these other properties is causative and proceeds directly. The has direct part were already returned as part of the default query. And then I told Gruff that, okay, when you graph the proceeds, so proceeds directly is a gist property that's between two events. And it's a temporal relation that means, you know, this event directly precedes this other event. So it's showing you a temporal ordering of the events. And so what I told Gruff is whenever you graph the proceeds directly links, I want you to do it in a left to right direction. And then the other thing I did is, you know, I expanded some of the nodes to show some of the additional nodes, you know, that correspond to the 3 properties that I've selected. And then I chose that node, purple node at the top center, that is sort of the parent node, and said, lay out the rest of the graph using a tree layout. And then I did just a little bit more manipulation so that I have that, you know, sort of the most important of all the nodes in this graph is the one that's in the upper right corner here, because that's showing you the result of this whole thing. That you know, it started by a bunch of nonsense conspiracy theory that was generated about how the lockdown from COVID, that part of the agenda of the people who support doing something about climate change is to institute a permanent lockdown, you know, due to climate change. And that conspiracy theory was then picked up by outlets like Fox News, figures like Laura Ingraham, and then their work was then picked up by some politicians who, you know, are essentially in the pocket of oil and gas companies and other people with the agenda to block climate change, and they use this as a part of justification to block the green recovery policy that was going to be part of the 2021 bills that were passed by Congress. So this is showing you, you know, what a lot more information that you can get with just a few manipulations of the knowledge graph. Another thing you can do with the knowledge graph that's really useful is many of those nodes correspond to documents. And so if you want to actually see, you know, the source document itself, it's very easy. That's one of the many menu options that you get from Gruff is there's a particular keystroke you can do, and then it'll take you to a URL that is associated with the specific node that you're on. And if it's a document, it will take you, you know, to the URL for that document. And there's other things that it can take you to that can also be useful, but that's the main use. And so what you're seeing here is each one of these web pages that I've got a screen capture of here were the result of clicking on some node in a graph in Gruff, and then using that option to visit the URL for that document. Okay, now the final thing I'm going to talk about is how we modeled some of the climate obstruction theories. And the first one, and this was the most straightforward one, is there's a greenwashing model that the CSSN has developed. I'm showing you the start page for this for that greenwashing model here, and I know it's probably hard to read it, but if you look at that page, you will see three buttons at the bottom called impact, alignment, and communication. And so each one of those is a subtype of greenwashing. And if you click on any one of those buttons, then you'll go to another page that has more subtypes, of that particular type of greenwashing. So this was really straightforward because it mapped really cleanly to just a class hierarchy. So what you're seeing over there on the right is that's the protege model that we created that corresponds to the CSSN greenwashing model. So we have the three top level kinds of greenwashing: by alignment, by communication, and by impact. And then we have each one of the subtypes, which you can't see, but if you went to that page and visited it, you would see each one of those have a description, examples, and so on, and that they correspond to the class hierarchy that's here. The second model, this is from one of Robert Brule's papers, is called an influence model. And this graph is from one of Brule's papers. He generously gave us the permission to reuse it. And you can see that in the graph, most of the nodes correspond to some type of either individual, some person, or some organization. But there's a few that don't, like public agenda and policy outcome. So we had to do some knowledge engineering, to tease out what is the meaning of this graph. The other thing about this graph is this is really a meta model. So this does not describe any specific example, of a flow, starting with money from a corporation and then going to a think tank and then creating, then maybe going to a lobbying firm and creating things that are picked up by the media and so on. This shows you that the abstract model of how that works. And what I showed you in the previous slide was instantiation of that model. And this shows how we modeled that model with classes and properties in Protege. So we created a subclass of event called influence event so that we could group all of the influence events under one class. And then we used multiple inheritance because most of the, but not all, but most of the influence events were also some subclass of a communication event. So in this case, like create advertising campaign is also a subclass of advertisement event, and advertisement event is a subclass of communication event. And then there's various axioms, that show like comes from agent, goes to agent, and so on, that we, and I think all of those are all in GIST as well. We use those to model the things that were in that previous graph and the way it was described by Brule in his paper. And specifically, if you look there over on the right, we created this property hierarchy. So the different kinds of influence, like something that comes from an agent, is like someone who creates a document, someone who gives money to a think tank, someone who publishes a document, things like that. All of those are subproperty of a super property called has cause. So now what we can do is we can take these different kinds of influence, and we can also just map the causal chain from one starting from a starting point of which is usually donation from a corporation to an endpoint which is usually some political outcome, and all of the links in the graph, in the chain, that go from the start, to the end, using this super property has cause. So we're following the causal links. And then finally, the other thing that we did is it had another super property. So this is a transitive super property, we call has cause transitive, because sometimes we may want to take a particular object and not just find the things that it directly caused, but the things that were caused by the things that it caused, and then the things that were caused by the things that it caused that then caused other things, and so in other words, if you want to find from any specific event, all of the transitive closure of all the events that were ultimately traced back to that event, you can do that with has clause transitive. And you think back to that graph that I was showing you in Gruff. Actually, what I used in Gruff is I used the inverse of this. There's a corresponding inverse property hierarchy. So the inverse of has clause is cause of, and if, in that previous Gruff graph, that was one of the major links that we used to show the causal chain from donation to ultimately a political outcome. And the final concept that we implemented is something called a field frame. This is also from some of Bruhl's work. And a field frame is essentially, it's a kind of belief system. And for this, I used some previous work that I did to represent beliefs in a social science ontology I created a few years ago. And in that ontology, I had the concept of belief and a subclass called belief system, which is just a collection of one or more beliefs. And then as I read about what Bruhl means by field frame, I realized, oh, well, what he's essentially talking about is a belief system. So I made it, field frame became a subclass of belief system. And you can see there, I've got a specific instance of field frame called the QAnon field frame, which has direct part is a gist property. And you can see the QAnon field frame has a number of sub parts to it. That are, let's just say, rather interesting, such as that JFK Jr. is still alive, and 5G and mind control and things like that. And finally, the last thing I want to point out is I used, and this is again from the previous work that I've done to model beliefs. One of the reasons that it's so hard to model beliefs in OWL is because each person is going to have contradictory beliefs. But of course, in OWL, OWL does not like contradictions because it's a logical language. So a way I found to get around that is to reify, take the triples, reify the triples, and explicitly model them as values of annotation properties. And I use annotation properties because in the previous work I actually did punning. And I find that punning can sometimes lead to weirdness, to use a real deep technical term, but it leads to problems that can be hard to debug. And I found that using annotation properties is just so much easier. You don't have to worry about creating puns before you start asserting things, and you don't have the potential problems that can be very hard to debug because they tend to come up when you're using multiple tools, like going back and forth, which I do a lot, between creating an ontology or editing an ontology in Protege and looking at the knowledge graph in Allegro graph. And I like to go back and forth, but I found that when I do that, everything works fine, except for puns tend to cause bugs that are fairly difficult to debug. And honestly, I've never even bothered to debug them. I just realized, what? I'm just going to go to annotation properties. And so anyway, that's why I use annotation properties here rather than punning. Okay, and then the last thing I want to show you is, and I think this is one of the most interesting things that we've done so far, is not only is this a tool that social scientists can use, but it's actually becoming a real model that can now do essentially, you can make falsifiable predictions. So like what I did is I went and I searched the internet and I found 5 or 6 examples that I thought were greenwashing that I knew were not in the current knowledge graph. I reasoned beforehand, okay, well, I think this is this kind of greenwashing. I gave the example to ChatGPT using, now this is using a different interface than the one I showed you before. This is an interface that is actually part of the Allegro graph interface. Uh, for reasons that I'm not going to go into, but for this kind of deeper kind of reasoning, this interface was better than the previous interface, which was more used for just finding documents that are related to a specific question. But to do kind of reasoning, like here's a new example of greenwashing. What kind of greenwashing is it? The chat interface is much better, and you can see, it gave me a very very lengthy answer, but at the very bottom, it did give me what I was really looking for, which is it says it's inconsistent organization in practice under greenwashing by alignment. So remember, classes and subclasses. So inconsistent organization in practice is one of the subclasses of greenwashing by alignment. And that was the prediction that I made of where I thought this new example of greenwashing would be classified. Now, obviously, this is not, this is anecdotal evidence. This is not valid, good scientific evidence for several reasons. First of all, because I did it and I'm biased, and second of all, so we what we really want is we want social scientists who know this stuff and who don't have a vested interest in the tool to give us those predictions, and then we want to see how it does, and we want to do more than just 6 examples. We want to do several examples with statistics and all that kind of cool stuff. So that's future work to be done. But the point is that I think even this, these anecdotal 6 examples that I've done so far, I think they're very promising, and that they show what can be done by integrating these two different kinds of reasoning, the deductive, logical, explicit knowledge representation of OWL, and the inductive, experience-based reasoning of a large language model. Okay, so finally, I'm just going to wrap up. Next steps, I kind of already covered this, is actually, I forgot to put, the most important next step is we want to get some funding. So all this work so far has not been funded at all. We just did this because we thought it was interesting and we thought it was a problem that was worth working on. And so first step is we'd like to get some funding, because I'd like to put it out on the internet so that social scientists can use this and give us real feedback. But to do that, I'd like to get a little bit of funding if possible. And then the next substantive step is to do actual user testing with social scientists, things like, test how well the system can make predictions, such as greenwashing. And then the other thing, this is a bit of a tangent, but one thing that I found when I made a RAG system using Allegro Graph on a previous domain, a completely different domain, is that, it shouldn't have been to my surprise, but it was kind of to my surprise, just because I expect, when I create an ontology, I just expect that, the system's going to have that knowledge in the ontology. But of course, the LLM does not have that knowledge. It only has the knowledge that is stored in the corpus and modeled as vectors. So to give the LLM the information that is in the ontology, what I did is I went and, I took all of the classes that I thought were important for the LLM to understand, and I put long text descriptions using the SCA's definition annotation property, on those classes. And then I, in that interface I showed you earlier, the SCA's definition property was one of the ones that I included in telling Allegro Graph, go and find all the values for this and create vectors for it. And I think it would be really interesting to and useful to generate those definition values automatically. And I don't think it would be that hard to do. So, this would be, I think, number one, this would be useful for all ontologies, because it would be a nice way to get a head start at doing your documentation. You can at least get an initial definition generated for you. But of course, it's especially useful for neurosymbolic systems, because that's one way of communicating the information from the knowledge graph to the large language model. I should say it's not the only way, and in fact, there's much more complex and sophisticated ways of doing it. And I may be an outlier here, and I may quite possibly could be wrong, but from what I've looked at so far, I actually think that actually I find this is often the case that the naive and simple way of doing it, in my opinion, looks like it's not only is it easier, but I think it's actually better to do it. So this is the naive and simple way. There's more sophisticated ways where you're essentially doing kind of the equivalent vector analysis of the graph itself. Um, uh, so that's another alternative way to do it. Who knows? Right now, I don't think anyone would say definitively we know which is the best way. But I do think it's an important problem. And if we could do this NLP generation, it would make testing out my hypothesis. This is the best way to do it a little bit easier to test. Okay, that's it. Thank you for your time. First of all, I really want to thank the undergrad data science interns who played a big role in this project. George Gino, Jacob Gino, and Adarsh Balaji. These guys were all taking a full course load, studying data science at different universities. They were not getting paid. They were not getting any class credit. They'd all done work with me in the past where, via programs where they did get some class credit by working with, quote unquote, a professional. But in fact, each one of them came to me and said, "Hey, you got any other new things to work on?" And if it hadn't been for that, I never would have even done this. So I cannot express how grateful I am to these guys, for taking time out of their extremely busy schedule while they're taking full class loads to be incredibly helpful in terms of the Python coding, that they did for this. So thanks, guys. I also want to thank Dr. Robert Brule. I've mentioned him several times. He was very helpful in providing resources and helping me, answer questions that we went back and forth a few times in email exchanges. And I want to thank Dr. Robert Netches, who always is someone who I turn to when I'm not sure how to do something and when I want guidance. And like Bob has many amazing properties. He can take something that it will take me 20 minutes to say and say it better and clearer in 2 minutes. And then finally, I want to thank people at AllegroGraph for their support in helping us use their neurosymbolic architecture, and of course the Protege team at Stanford and everybody on the user support list for Protege. It's one of the best groups I find for getting support. Okay, thank you very much, and that's it.